All right, folks. Let's get started with our lecture content for today. Thank you all for making it to the classroom. So today we're going to continue our discussion of rendering. Not a terribly big surprise, and extend our discussion of rendering to global illumination, which is sort of an effect we've alluded to a number of times. Remember, global illumination is like the effect of light bouncing off of stuff into other stuff, which we've only dealt with in the context of like perfect, like nicely reflective surfaces. So today we're going to deal with all these nice, like kind of glowy style light effects, as well as things like magnifying glasses that can focus light, and all these kind of nonlinear effects that the ray tracing pipeline, as we've described it so far, doesn't really handle in a nice or particularly elegant way, right? And the basic issue, to recap a little bit, is that ray tracing doesn't, the name is a little bit suggestive, but it doesn't actually do what you might guess, which would be trace rays of light. Rather, it traces rays from your eyeball to the light, which is not physics, right? That's like backward from physics. It's basically making use of all these nice symmetries we have. But certain effects, that path from your eyeball to the light is kind of hard to find, and those are exactly the ones that ray tracing is not particularly good at capturing, right? And so today we're going to add to that techniques that do other stuff, like trace rays of light from the light bulb into the scene, and then try to use that to inform how you do your rendering, which of course is going to add many more rays that we have to trace in our algorithm. And so what do you think the result of these algorithms is going to be? Yep, they're going to be hella slow. And that's actually still true. Like if you download, I don't know, Mental Ray, whatever your favorite ray tracing tool is on your computer, and enable global illumination, you'll get beautiful, if not usually somewhat noisy images if you don't control it the right way. And you'll have to wait a very, very, very long time to get them, even with all these cool acceleration data structures that we've already talked about. So today, essentially, the big thing we're going to do a lot of is random number generators. And this is just true in general. I mean, we'll see in just a moment that we can think of all of rendering as computing one giant integral, which I know is everybody's favorite task. And because of that, a very typical way to approximate integrals computationally is to like throw darts and then average. This is, like for example, if you want to, I don't know, estimate the area of a circle, what could you do? Like throw darts at a square and count the number of times that it is inside of a circle, and roughly that fraction multiplied by the area of the square is the area of the circle, yeah? So those sorts of strategies are used all over the place in ray tracing, because with these extremely complicated functions that we have to integrate, and unlike all the cool integration tricks you do over in the math department, these things don't have closed form solutions, right? So the best we can do is just a bunch of numerical stuff. By the way, just for fun trivia fact, the noise pattern in the back here, right? So you've probably taken a probability class or encountered probability a little bit, right? How many of us think, so this definitely looks random. Do you guys think this is uniformly random noise? In other words, like I just keep randomly drawing x and y coordinates uniformly between 0 and 1 and then just plotting a point? No, these are really nicely spread out points, like suspiciously nicely spread out. And it turns out that this is sort of a very typical trick that's going to happen a lot in rendering, is that like on the one hand we want randomness, on the other hand random numbers actually tend to cluster together more than our brains like. And so oftentimes we'll use things like blue noise, like white noise is purely random stuff. Blue noise is where there's some correlation between your samples, to get sort of nicely spread out yet still random distributions. So a fun probability question for you guys to think about in the back of your head while we talk about a lot of other stuff. How would you generate a pattern that looks like this? Right? And it's actually not so easy, right? Because in order to make something that looks like this, somehow the location of one point now depends on the locations of the points nearby. So like uniformly random sampling doesn't work. But anyway, fun problem. Okay, so but today, most of our focus is going to be in global illumination. We're going to talk about the rendering equation. That is, you can actually think of your rendering software as trying to approximate a solution of one giant equation, which is kind of a surprise, although it's kind of a brain-dead equation, so it depends on how you think about it, I suppose. We're going to talk about path tracing, which is one particular technique for dealing with global illumination, and then some other kind of variations on the path tracing story. And then we're going to step back 10 feet and say, like, okay, all of these things are just trying to compute integrals. So we're going to do kind of a little bit of a sideways shuffle and say, we've seen integrals all over the place, right? In our last lecture on anti-aliasing, we also want to take integrals, in that case in screen space. Here we're going to do them in 3D space. So maybe it's worth kind of just thinking about integration algorithms a little bit orthogonally to all these graphics tools for a little bit. So we'll discuss some of these ideas and then link them back to rendering at the end of the lecture, time permitting, because as always, I talk too much. Okay, so our big focus today is on global illumination. Basically, so far, all we've seen is direct lighting, right? So like the ray tracers that you guys hopefully all turned in yesterday at, what, 6 p.m. or whenever they're due. Essentially, when you saw a color on a surface, the reason you saw it was like the result of like a direct path between your eyeball and the light that only went off of one of two things, right? Either directly off of a diffuse surface or off of a surface that was like purely reflective, right? But the reality is that in global illumination, you know, like if I'm maybe looking at the corner of a room and I have a light bulb, right? And I look at like the light shading on the bottom wall here, part of the reason that this thing is receiving light, it's not just coming directly from the light bulb, it's also maybe bouncing off of the floor and onto the wall. And so far, our ray tracer really hasn't accounted for that effect, right? And indeed, it's pretty reasonable why it hasn't, right? Because like, what would you not want to do is like integrate over the entire floor to get exactly the right color at this point, especially because probably that effect is pretty minor, right? And so global illumination is one of these subtle effects that is going to make a pretty perturbative change to our image. Like, there's not going to be a huge one, except if you, like, okay, you can design images where it is a big effect, but typically it's pretty subtle. But in order to achieve it, you want to multiply your computation by some huge number. So in any event, that's our basic goal today, is to deal with these indirect lighting effects. And in practice, the way that we do that is by sending less and less arrays. So here's an example of an image. Here's our favorite box with 2 balls in it. Anybody remember what this thing's called? Darius does not. Yes? The Cornell box. Now he does. And you just studied for your exam.
I didn't actually study. I learned it off the top that it wasn't that.
You're killing me. Okay, but in any event, this kind of image is generated using the sort of machinery that you guys already know how to do, right? And you can see that you can usually spot these images by looking at things like, you know, the shadows are all pretty sharp here. There's no, notice that the wall is red, but it meets into the white floor, and there's no red on the floor, right? Because the only source of red color would be the light bouncing off of this diffuse wall and then hitting the ground, which is this kind of subtle effect. So if you include global illumination in this particular scene, one thing it does is just brighten up a lot, because essentially you're accounting for more light than you had before. But you can start to see some additional effects. And by the way, today we're going to, I encourage you guys with laptops to load up the slides and kind of look at them, because it's a little bit hard to see on the screen here. But for example, if you look very closely, there's just a tiny tinge of red on the floor now. There's soft shadows. Now this glass ball is focusing the light underneath it. And these are the sorts of effects that we're after today. Yes?
Is that refraction of like the green wall, or there's like a little spot of light?
This little thing?
Yeah.
Yes? I think.
Sure what.
I don't know. Maybe what's going on. I'm gonna get it wrong. My best guess would be maybe like there's like some small amount of light that's coming in and then doing total internal reflection and then reflecting that way. But I don't know. I could be making that up. Yeah. Yes.
What is the distinction between this and the ambient lighting?
Ambient lighting is the technical term for that is a hack, right? Is essentially we're just like pretending like every surface in our scene like weirdly like emits a little bit of light, right? But like you didn't do any kind of lighting computation when you did ambient lighting, right? You just kind of added a constant. But if you think about it physically, like if you had an ambient color for a surface, what would it mean? It means when I turn off the lights, that surface, I can still see it, right? And so something went wrong. And essentially, it is a reasonable question to ask, because in some sense that ambient color is used in part to account for this issue, right? Because otherwise scenes would be awfully dark. That's absolutely right. Okay, so how can we explain this mathematically, which of course is my goal in life? Essentially, when we use the BRDF, we kind of use it in a weird way, if you think about it so far, right? Because the BRDF, there's that, what does the D in BRDF stand for? Anyone remember?
Directional?
Directional is not actually correct. There is directional in it, but it's part of the B, right? It's bidirectional. Yeah, gotcha.
Bidirectional, reflectional, directional.
an interesting theory. Does anybody have any other proposals? Distribution. Yeah. In particular, what is the BRDF? It's saying if I have a unit of light that comes in this way, what is the distribution of the light energy getting bounced off of the surface as a function of where I am on probably this half sphere? Unless the surface is transparent, then maybe it goes through, right? Have we used a distributional property at all? No, right? We've just kind of evaluated it on one ray and used that for our shading computation. But really, what this thing is sort of suggesting is that we need to do an integral over the whole surface of the sphere to account for all the possible incoming light and all the possible outgoing light in a careful way, right? And so that's what global illumination is really trying to do, is to sum over the entire hemisphere as if every single possible incoming direction is a potential light source. And so this was originally noticed back by Kajiya, I believe. And he expressed this in a very famous equation. This is the, I think, reflectance equation, or sometimes rendering equation. And the basic idea here is, let's see, so L is a vector that's on the half sphere here, right? And so let's read what this equation is saying. It's saying that I'm sitting at a point X, that's like the center point that's emitting light here. And the question is, how is it emitting light? Well, really, it's one term, or we'll see maybe the sum of two terms, depending on whether this is a light bulb or not. But let's say it's not a light bulb, so it's just a surface that like light bounces off of. Well, how does light bounce off of work? Well, for every possible incoming direction, I have to account for the BRDF, which is saying for this amount coming in, how much goes out toward your eye, right? So that's an integral over the whole surface of the sphere, right? So for every possible incoming direction L, I scale the amount of light coming in direction L by the BRDF, which is a function of where I am, the incoming direction, and the outgoing direction. And that's the amount that goes out in the direction V here, right? And so what is this saying? This is saying the total amount of light that comes out at V is basically just the integral over all the possible incoming directions scaled by the BRDF. Does that function make sense? This is where that D comes from, right? Because this is it's like a probability distribution. Right? It's a distribution of light. Right, and that cosine term is just due to the fact that light falls off as you know, depending on the angle. Okay, so right, so this is the reflectance equation, but there's a bit of a problem, right? Like you could say, like, okay, so what should ray tracing be? Like maybe it should be just like evaluating this integral, and in some sense that's what ray tracing is. Here's the problem. Let's say I have two walls in my room. Well, this wall has a vector pointing to the other wall. The wall on the other side has a vector pointing to the first one. So what does that mean? That means this guy's out affects this guy's in. This guy's out affects this guy's in. So this is not just an integral that I can evaluate. It's actually a system of equations. Do you see that? At every possible point, there's this L out and L in function, and they're all defined in terms of each other by this relationship here. And so if you really wanted to render with 1,000 gajillion% precision, you wouldn't be doing what we're doing right now, which is just like bouncing rays around and collecting colors. You'd have to actually solve a system of equations, extremely nonlinear one. And well, is that right? I guess maybe it's linear if you know your BRDS, but it's a really big one. And that's a very hard thing to do. Right? So again, like where does ln come from? It comes from someone else, and that's what makes this thing so messy. Right? This is what makes rendering hard. Yeah? And so essentially we can understand everything we've done so far as an approximation in the regime where essentially the in here you're just assuming is 0 for anything that's not a light source, right? That's what our ray tracer has done so far. And why is that? Well, in that case, this integral is not so hard to compute anymore. It's just like a delta function. Okay, so, but incidentally, of course, on a light bulb, you need an additional term, which is just the emitting stuff. Okay, so this is just one giant recursive relationship. Incidentally, if you're into integral equations, partial differential equations, all that stuff, this is a really nasty one and one that is very poorly understood in theory. Okay, so right, this goes back to Kajiya and company in the 1980s, which, by the way, in graphics is fairly recent for something that's like this fundamental, right? Like you didn't need a computer to discover this equation or try to analyze it. But it is kind of nice that this rendering equation is what's really describing what's going on when you're trying to draw a scene in completeness. The only problem is that we can't actually solve it, right? Because this is a relationship between functions on the sphere at every single possible point of my scene. This is a very, very complicated equation. Okay, right, and so essentially, no analytic solution is possible, and so what we're going to try and do today is to come up with different Monte Carlo techniques that maybe try to evaluate these integrals, and the way that they're going to do it is like, what do we do when we ray trace? We ray trace out to our eye and a surface. Now rather than just bouncing off and sending one ray, we're going to send a bunch of rays over the sphere, but then what's going to be the problem? Those hit a bunch of surfaces. Those ones now have to send out a bunch of rays over the sphere. But what we're going to do is we're going to assume that the BRDF is such that after maybe 1 or 2 bounces, essentially the contribution is 0 for anything that's not directly lit. Right? And that's what's going to make this thing finite. Yes?
So when you say like assume the BRDF, does that mean that we're like coming up with like some function that's approximating the BRDF, or is that something that we're given?
That would be something you're given, right? I think, and which I think is realistic, right? Like typically when you're rendering a scene, you know the materials of everything you're rendering.
Yeah.
And so that's the sort of assumption here. There's a different question, which is how do you measure a BRDF? That's a hard question.
Okay.
Yeah. I think all the BRDFs we covered in this class are kind of phenomenological. Like we noticed that surfaces have lobes that kind of look like that. If you want to be a physicist about it, it's quite challenging. Okay, and so there are a lot of different ways to solve these equations. We're mostly going to focus on Monte Carlo techniques. Monte Carlo is a place where gambling happens, right? So this is Monte Carlo algorithms are like randomly generate a bunch of rays, average stuff. There's a whole other set of algorithms out there that are called radiosity. These are not particularly popular at the moment, although all these things come and go. Radiosity does kind of an amazing thing, which is it tries to take the rendering equation, discretize it like you would discretize any other equation, like the wave equation or like fluid simulation, and then solve it with a capital S. These are cool in theory, but I think are quite difficult, although there are certain sort of radiance transfer techniques where this is helpful. Okay, so today we're mostly going to do practical stuff instead of worrying a whole lot about the theory of the rendering equation, which could easily fill an entire course and still get nowhere. Integral equations are really fun, by the way. I love studying that stuff. Okay, so right, so let's talk about global illumination. What are we going to actually do? So the sort of typical strategy in this area, these Monte Carlo techniques are actually not so complicated to understand or to implement. Like it's a pretty small extension of the ray tracer that you already have. It's just that it's slow, right? That's the typical thing that happens in ray tracing. And so what we're going to do here, so as usual, we're going to trace a ray from our eye into the first thing that it hits. But now, in order to really get that light out, which is the light into your eye, what should I do? I should send out a bunch of rays along that whole hemisphere, collect their light in, scale them by the BRDF, and sum them all together, right? That's what that rendering equation says. So in Monte Carlo ray tracing, that's exactly what we do, right? We just send out a bunch of rays from this point because we're going to try and approximate that integral over the hemisphere, and that's the number that we're going to do. Now, what's the problem? Well, this is recursive, and in fact, if you believe the rendering equation, that recursion will never end, right? Because I could just sit there and bounce back and forth between two surfaces, and at least in theory, I guess, unless you believe in quantum light stuff, where maybe at some point it just goes to 0. Like you could just sit there and keep summing this thing together with a discount factor. The reality is the BRDF is typically less than 1, meaning that light comes in and the amount that comes out is less than what came in, which I think is true for most surfaces. So what does that mean? That means after a few bounces, really nothing significant is happening, right? And so a very typical thing is, just like you already implemented in your ray tracing assignment, you just limit the depth of your recursion, and at some point you just maybe return like the diffuse color of your surface, reflected against the direct lighting from the light bulb, because that's going to dominate by far any indirect effects you get from global illumination. That make sense? Yeah.
Are we going to send out completely random beams, or are they going to be distributed according to the theory?
That's a good question. The answer is it depends on your ray tracer. Yeah. So the question was, do you just randomly distribute stuff everywhere on the hemisphere? It could be that's the right strategy. So for example, it might be that I have a BRDF with a giant lobe this way, but for whatever reason, I have a really, really strong incoming directional light source over here. And it's so strong that it actually is worthwhile to send more rays toward the light and not worry about the BRDF, even though the discount factor is big. But there's a chicken and egg problem. How would I know that? Well, I know that by ray tracing, which I can't do because that's exactly what I'm trying to carry out. Yeah. Okay, so right, so this is the sort of Monte Carlo ray tracing approach, right, and then you can recurse as you bounce. Here's the thing. So let's say that I use 10 samples. By the way, 10 samples to evaluate an integral over a whole sphere is pretty darn small. So if I have 2 bounces, that means how many computations am I doing per pixel? 100. Yeah, 10 squares, 100. If I do 3 bounces, then 1,000. This is all for 1 pixel without anti-aliasing. So maybe I throw 100 samples for my anti-aliasing in there. So now I'm up to like, what, 10,000, 100,000. That's a lot of computation for 1 color. And so that's where things, that's why global illumination is so crazy, right? Right. One small fix that people typically do in global illumination, the best thing you could, somehow the gold standard would be you just sit there and bounce rays until the cows come home. The reality is that, of course, the dominant source of light on any given surface, except in very, very specific scenes, is like the bright light bulb that's pointing right at it. So a very typical thing to do would be to, in addition to doing that integral over the sphere, explicitly send 1 ray toward your light bulb, because you know that's going to be where all your light comes from. Okay, that's a pretty sort of typical approach. And here's what it looks like. So here is a scene with global illumination. First, what are the pluses? Well, if you look, you got that nice little red and blue tinge on the floor, just barely. You got to kind of get up in its business to see that color. What's the problem here? Yeah. Super noisy. Why is that? Any guess? Either one of you. Let somebody speak up.
You're sending rays randomly and stuff in that randomly.
Yeah, so in particular, let's say I'm rendering the floor, as I like to do. So I've got this floor, I stick a little hemisphere on top of the floor. I start randomly generating ray directions, maybe 10 of them. Now, there's an issue in this Cornell box. The Cornell box, by the way, is designed to be evil for rendering, right? It's like this innocent looking scene that like shows you everything that goes wrong. There's a special thing about the ceiling in this scene, namely that it contains a light bulb. And let's say the probability, so let's say I place a little hemisphere here. We're going to ignore these 2 balls for now, they don't matter. And I randomly draw uniformly the direction on the upper half sphere. And I send a ray out in that direction. I would say the probability of hitting that light bulb is like what? Roughly maybe 1 in 8-ish. It's about 1/8 of the ceiling here. So what does that mean? That means for every 8 rays that I send out, with some probability, 1 of them will hit that light bulb, and it's going to return a color that's way brighter than the color I'm going to get for all my other rays in my weighted average. Does that make sense? So if I only send out 10 rays, in fact, let's make it even. Let's say that I send out 8 rays for my secondary bounce, right? Most of my pixels, on average, will have 1 ray that hits the light bulb. Every once in a while, a pixel, when it's doing that little integral, it's going to have 2 rays that hit the light bulb. What's going to happen to its color? It's going to get way brighter because we're dealing in factors of 1/8. That's pretty big relative to the color. Yeah? Similarly, every once in a while, I'll send all 8 rays and none of them hit the light bulb, and then what's going to happen? It'll be super dark, right? And these are completely just randomly generated at every point, and that's exactly the noise that you're seeing here. Yeah? And of course, these effects only get worse as you, add reflection, refraction, all these kinds of effects, right? Because now there's just all kinds of nonlinearities hiding in your scene. So we're going to return to that. We're going to keep that in the back of our head. Moreover, there's a second issue, which of course is that this algorithm is ridiculously slow. One typical thing that people do, which is sort of a good key phrase to know in graphics world, is something called path tracing. In path tracing, this was, I think, designed actually by the original people who proposed the rendering equation. It's kind of a clever trick where what you do is when you send out your sample here, what's the world's simplest approximation of this surface integral? It's literally randomly generate 1 ray and then just assume that's the integral over the whole sphere scaled by the BRDF. Yeah, so that's what do you call that in calculus class, right? That's the rectangle integrator as opposed to Simpson's rule or whatever. So in path tracing, this is this really weird, bizarre kind of brain-dead algorithm where literally this algorithm that I've sketched out for you guys, you only ever send out 1 bounce. So like I send my ray out here, Then I bounce it, I bounce it, I bounce it until I hit my recursion limit. I compute the color, and then I kind of work my way backward. And I get a stupidly noisy color from my pixel. But I'm going to anti-alias my pixel anyway. So what am I going to do? I'm going to send a bunch of rays out of my eyeball through that pixel and average the result. And the basic point in path tracing is that you might as well do your averaging at the level of the pixel sample rather than at the level of every one of these spherical integrals, because they're going to contribute such a tiny term to your rendering anyway that the principal effect is happening all right at this point. It's kind of a clever trick. So we'll see some pseudocode for a second. So essentially, what path tracing does is it accounts for the noise in these integrals at the anti-aliasing level rather than trying to approximate these spherical integrals in a clever way. Does that make sense? Right, so in other words, it's just one path. So here's some pseudocode that I added at the last second on the slides, and I'm realizing now is way too small for you to read. So maybe you can look at it later, but essentially the point here, you send out one ray, that's it, and now you send out one secondary ray, and then you work your way backward. That's what these three pieces of code are doing. Notice there's no for loops here. And then the only for loop is that when you're rendering, you send multiple samples per pixel. Yeah, so that's the kind of clever trick. In other words, all of these integrals are so noisy anyway, let's just embrace that noise and denoise just at the level of that one hit that comes out of your eyeball instead of all the other places you could. Any questions so far?
I mean, it's more just like, it seems like you're, when you do each pixel independently for something like global illumination, we're throwing away a ton of shared information.
Mm-hmm. Yeah.
Are there any techniques that are trying to sort of not throw? Or
there are. So let's continue. Yeah, that's exactly right. So Colton points out that, like, when I do this global illumination stuff, I'm bouncing rays all over the scene, and it could be that two of them end up in a very similar place. Maybe I should reuse that computation. He's absolutely right. So let's keep that in our head for a minute. All right. So here's path tracing with 10 samples per pixel. I don't know why you would remember the noise level in our previous image, but I assure you it's slightly less. In any event, let's say for fun, remember that I cheated a little bit, or rather Henrik cheated a little bit, and we replaced our two spheres that used to be shiny metallic balls, and we made them diffuse. What do you think is going to happen if I make them metallic? Yeah. Yeah, exactly. Now all of a sudden you've got like kind of spiky stuff every which way. And so here's the effect here, right? Because every once in a while, like your wall sends something that bounces off the sphere and hits the light bulb, and then suddenly that pixel gets way brighter. And this is the typical thing that goes wrong. Yeah? But if you add enough paths per pixel, eventually this effect goes away. Remember there's sort of two different variations on the same theme. One always sends a sample back to the light, one doesn't. And indeed, sending samples back to the light decreases the noise a little bit. By the way, these images we're going to show you today, the noise is exaggerated. The reality is that we would send way more rays per pixel than we are in the examples in this lecture, but then the images wouldn't be very interesting to look at. Right? So we're doing this on purpose. Okay. Incidentally, here's kind of a fun one. One key ingredient in our code is that we're using a random number generator. And it turns out, like, sometimes I forget if the algorithms class here covers random number generation or not. It's like kind of a weird universe, right? Because computers aren't very good at random stuff. You can imagine a universe where, like, maybe you seed your random number generator at the same thing at every pixel. Oftentimes, for a lot of computations, numerical analysis, it doesn't really matter. But it turns out in this universe, it actually matters a ton. So, like, here's an example where every single pixel has used the same random number generator, or like the same sequence of points on the hemisphere. What you end up seeing is that sequence of points reflected in your scene in a funny way. So all this is to say that the details really matter when you implement this stuff, which is disappointing. There's a really, really cool WebGL demo. I'll admit this morning I intended to try it and I forgot, but let's see if madebyEvan.com still works. I rely on Evan for stuff. Let's see here. So the neat thing is that our computers these days, it's like really a miracle of modern whatever, are like fast enough that you can do path tracing in your web browser, and this is actually like feasible, which like in my generation, it's just like, so I encourage you guys to play with this at home. So this person has set up this nice little scene. All these scenes are always like boxes with very bright light bulbs that are like, you know, weirdly diffuse objects, because those are the ones that make path tracing easy to see. So like here's this kind of fun demo. I can take my scene and grab it and rotate it and then just watch path tracing happen. And you can see the more samples that you add, you know, when you initially have almost, so here I'm moving the light bulb. When you don't have that many samples in your scene, you can see what happens, which is that you get random noise, which tends to look like the colors in your scene, right? Because if I only send out like one ray with like 50% probability to hit the blue side, 50% probability to hit the red side, or the yellow side rather. So then like what ends up happening here, you get like every other pixel is blue and every other one's yellow, and the longer I run this process, the more that gets smoothed out. So anyway, I encourage you guys to play with this at home. It's like ridiculously fun. Oops, here's another scene. I think you can play with the Cornell box too. There's the traditional Cornell box. Just for fun, let's make our mirrored surfaces. So when your surfaces are mirrored, one thing that'll happen is the convergence is a little bit slower now. Or here's, maybe we can add some spheres just for fun. Okay, so anyway, I can play with these all day. Right, so let's go back. Yeah, so, okay. Right, so there's all kinds of things online. PBRT is sort of a famous, this textbook I mentioned to you guys before, which is a textbook and a ray tracer at the same time, that you can just download and play with. Mitsuba is another one. There are a bunch of them out there. All right, any questions so far? Incidentally, this image is, I think, the first path traced image. It's kind of a funny story behind it. So I think it came out in 1986, and then about 10, 15 years later, they wanted to do a retrospective and rendering at the SIGGRAPH conference, and somebody tried to reproduce all the kind of famous rendered images, you know, write all the code, I give you stuff to play with, and nobody could reproduce this image. And it turned out that Kajia had a bug, and all the figures in this paper were incorrect. But it's the method we all use now. And is a valid method, he just had a bug in his code. And that's actually a thing that happens a lot in rendering, because it's very hard to detect bugs in your code. They just make little subtle, especially in path tracing, there's just little subtle changes that probably look fine. There's sort of a nice question, right? Like, does it, if you can't detect the bug, is it a bug? Yeah, I don't know. Okay, so returning to Colton's question here, of course, path tracing is extremely, extremely costly. We need a bunch of rays per pixel, and then every time we start a new pixel, we just threw away all our old rays and we're going to start over. That seems like a lot of extra work. So even though you know, we could get these nice images, we're doing a ton of computation for what really is a subtle effect. Okay, so in order to see that better, one way that you can do that is render your scene twice, once with global illumination and once without, and then subtract those two. And here's what that looks like. So this is just the effects of global illumination. You can see, right? I mean, there's like mostly just the highlights of the image. The thing to notice is that relative to the original scene, the global illumination part of our scene is fairly smooth, which is weird in rendering, right? Like when you render images, they tend to have like lots of sharp edges and all that stuff. The global illumination part of stuff, it's like mostly kind of grayish. There's just like small changes as you move along the image. That kind of makes sense, right? It's just a secondary effect. And so the typical kind of idea of ways to accelerate this technique is to say, like, well, if it's so smooth, right? If it's basically some kind of low frequency signal, I shouldn't need as many samples. Like, I shouldn't need a bunch of samples per pixel to resolve this thing, right? Maybe I can just do like a low resolution rendering of the indirect lighting and then just scale it up and add it to my high resolution rendering of the direct lighting. Put those two things together, and perceptually I'm not going to notice a difference. And so a bunch of different algorithms are all built on that basic observation. So the one that we'll mention first is something called Irradiance caching. This is more or less what your colleague just suggested a few minutes ago. So in Irradiance caching, here's a basic idea. You know, so I go ahead, I'm doing my path tracing algorithm. I send this thing out. He sends out all of his secondary rays, does some expensive computation. Now I render another pixel, and he sends out something, what I'm going to do is rather than just throw away that computation for the indirect light at this pixel, I'm going to keep it. I'm going to keep maybe the list of outgoing rays and the colors that they got. And now, let's say that I render this orange pixel, which is somehow halfway between these two guys. What do you think I'm going to do? Just going to borrow these two guys' list of colors, maybe munch them together somehow, do a little bit of averaging. And then rather than doing some expensive path tracing thing where I send out a bunch of secondary rays, I'm just going to borrow those guys' secondary rays to render this orange pixel and pretend like it's probably close enough, because nearby pixels get similar indirect lighting. Right? And so that's the idea of irradiance caching, which is that I basically proceed as normal in my rendering algorithm, right? My path tracing. So I keep sending rays out but I'm going to say, if there's no yellow sample nearby, then I just do what I did before. I do that secondary integral. If there is a yellow point nearby, I'm just going to borrow his integral instead. Typically with a little bit of averaging to smooth stuff out. And so that's the nice effect. Usually people still do the full calculation for direct lighting, because again, that is the main source of interesting signal in your image. And it's just one calculation per light. Like, it's not like a whole integral you have to compute. So an image I see, here's an image of what this looks like. So like here, we've rendered the Cornell box, and then what's going on is you send out your ray, it looks in a little neighborhood around that in the 3D scene. It says, okay, if there's not a cached point, then I'll just make a new one and put it there and do my calculation. And otherwise, I'll just grab stuff from nearby. And so what you end up with is this sort of scattered set of points. Some very typical things to do in the Irradiance cache, which is this list of points, is maybe you also account for something like the normal of the surface that it's bouncing off of. Like, notice that there's higher density of points at this corner, because that has a pretty serious effect on shading, right? So it may not make sense to reuse the samples when that happens. Your question? Happens. Okay, yeah, so that's Irradiance caching. It's a clever algorithm. And again, notice that these are all just like small improvements on the last guy's algorithm. Notice that the amount of memory that I need when I run an algorithm like this is much larger, right? Because now I'm storing a bunch of information. Moreover, what's going to happen? I send a new ray out into my scene, I hit the wall, and now I have this new line of code that says find things in the Irradiance cache that are nearby. If my Irradiance cache has 1 million points in it, which it easily could, that's going to be a slow thing in itself, right? Just answer the question, yay or nay, is there a nearby point in the Irradiance cache? How do I solve that problem? Cache the cache? That's, I don't know what that means, but I like it. I want like a t-shirt that says that. Maybe for something more concrete. Somebody new, I know, because we've already covered this. Yeah. Yeah, we have a KD tree, or like one of these data structures that sort of accelerates searching for points in 3D space. Reasonable thing to do. All right, any questions? Yeah. Oh, I see what you're saying. Like these vertical lines here? That's a good question. I wonder, I don't know offhand. Like maybe what's going on is a lot of times ray tracers don't render rays in rows. Like they'll traverse the image in such a way so that your Irradiance cache is likely to sort of fill itself up in an even way. So maybe it like took some kind of path and somehow moved in columns there. Yeah, I'm actually not sure. It's a good question. No. Any other things I can not answer? Cool. All right, here's sort of the original Irradiance thing historically, if you're curious. Looks like a very dated web page. Any questions so far? This is a rendered image, by the way. Yeah. Cool. All right, here's another kind of buzzword, graphics world you've probably heard of. This is called photon mapping. Photon mapping and Irradiance caching are very, very similar to one another. Actually, before we proceed too much, Irradiance caching, well, actually, never mind. I was going to say something dumb, so we're not going to say that. Okay, so photon mapping. So far in Irradiance caching, the rays still come from the basic ray tracing algorithm, right? Like I send rays out from my eye, and that's what's placing points in the cache. But in some sense, the distribution of indirect light maybe is better captured not by sending rays out from my eye, right? That's a very egocentric way to do rendering, But rather, like for instance, like let's say that I'm rendering a scene and like it's a giant magnifying glass and all the light is going down to a point, right? The irradiance cache actually might not capture that terribly well, right? Because I'm still doing it in screen space. A different thing that I could do, which is called photon mapping, is basically the same algorithm, but rather than generating rays from my eyeball, I'm going to randomly generate rays that start at the light bulb and then scatter them outward into the scene. Right, so I'm just going to follow paths from the light source, bounce them around, and then just keep where they ended up. Right, so for instance, in that magnifying glass, the ray would come out of the light bulb, and be reflect toward the point, and then you have a big pile of points in your cache right at that point where your magnifying glass focuses. This is different than your radiance cache, right? Your radiance cache would say, oh, I have one sample right in the middle of that thing. That's close enough, and leave it there. Yep. And so photon, I would say photon, the term photon here is extremely loose, but roughly you're just casting rays every which way from your light source, storing them in your scene, and now there's no reason why your photons have to be uniformly distributed with respect to your computer screen. They're uniformly distributed with respect to your light source. And depending on the scene, one of these can be more effective than the other. And just like before, of course, we would probably want to use one of these spatial data structures. Photon mapping is kind of interesting because one thing if you kind of think about it, like this is a pass that happens before you do any rendering at all. So it's kind of one of these interesting two-step algorithms where like, you know, somehow the cost per photon is divided by the total number of pixels in your image. Right, but anyway, the actual algorithm is pretty much exactly the same. So the difference in the photon mapping algorithm is that essentially, rather than randomly scattering secondary rays when I do my path tracing, now I randomly draw among the photons in my image because those are the ones where I actually have information. And that's what I use to generate my secondary rays. So this is something that this process is sometimes called the final gather. So like if you ever watch the progress bar in a render, that little phrase will pop up sometimes. So here's what this looks like. So on the left-hand side, we have the photon map of the Cornell box. You can see that like this is non-uniform with respect to the screen, but rather like it's kind of showing you where the secondary lighting is the brightest. On the right-hand side, we have the image. Of course, you can see, for example, like here's that focusing effect we were talking about before. Cool. Any questions so far? You can just remember that photon map, light bulb space, other one whose name I forgot, screen space, irradiance cache. Yes?
Here's how, like, so we're sending out, like, these photons randomly.
Mm-hmm.
Right? I'm confused about how it still knows to, like, do the focus.
Yeah, so I send the photon out of the light source, so that's up here. I still have to do tracing. It doesn't just land on that bulb and stop. I trace it all the way through, and then it lands on the ground. Exactly. Yeah. In fact, this is closer to the physics than the ray tracing algorithm, right? It's actually tracing the light. Yeah.
Thank you.
Yes.
So, for the non-photon mapping,
Irradiance caching.
irradiance caching, does that mean that like every frame you'd have to recompute this?
Oh, that's a good question. We haven't talked about animation. Yeah. So in photon mapping, for instance, if I like want to render a fly through of this room, and the room is stationary, there's nothing changing about it, then you're right. I could compute the photon map once. In fact, in real-time graphics, like if you wanted some global illumination, but you have a video game, most likely what you would do is offline, like at your video game studio before you distribute it, you would do this kind of rendering and then just store these numbers on your video game scene. That would be harder to do in irradiance caching because, of course, they're in screen space. So if you move your camera, all of that stuff changes. So I guess you could still keep it around, but it would be distributed in kind of a funny way. Yeah. Not quite. So the left image here is just the set of photons. That's just where the things ended up. The smoothing is happening here. When I render the scene, I look for nearby photons and I sort of average the result. Yeah. Mm-hmm. It depends on the photon mapping algorithm. In this case, white is actually correct because all it's doing is tracing from the light bulb to the first diffuse surface that it hits, and then just storing the fact that there's a path from the light bulb to that point. And then the material computation is happening later. Yeah. Any others? These are great questions. Yeah.
So for when you're doing the path tracing with photon mapping,
Mm-hmm.
and you choose a photon to bounce to
Mm-hmm.
that's on the hemisphere, does that mean that whatever that photon happens and has stored is basically just a fixed value? So you're essentially drawing from a set of photons that.
That's exactly right. So you're still evaluating that spherical integral, but what you're doing is like when you do the spherical integration, normally you just randomly draw points on the whole hemisphere. Now what we're going to do is restrict the set of points that you can randomly draw from to points that we know happen to land at these photons, because that's where we have information.
So the idea is that you don't have to do any sort of array there. It's just you're drawing.
Yeah. Although of course all these algorithms can be mixed and matched, right? I mean, maybe you do a little bit of one, a little bit of the other. Yeah. Mm-hmm.
So as for all of these, as the number of rays approaches infinity, are we theoretically guaranteed to do this reflection?
Guarantee is a strong word.
Do we approach it?
Yeah. Okay, if you take my measure theory course, then I would ask you the question, which is like, in what metric, you know? Are we talking weak convergence or strong convergence? Which is completely irrelevant in rendering because we don't get anywhere close. I don't think they would necessarily approach this. Well, I guess it depends. If you set up your math really, really carefully between two of these methods, you might be able to convince yourself they approach the same thing. The reality is that they typically are hacked together every way but Sunday, and probably lots of approximations happen that are kind of specialized to these different algorithms that are make them slightly different from one another. I mean, this whole process of rendering is a little bit unnatural, right? It's not like some of these physics ones where like you just have one PDE, ODE that you're trying to simulate, and you just have to show that as your spacing goes to 0, this thing converges. We're making approximations everywhere here. It's not like there's just one equation we're trying to solve. And so in a system that's complicated, I hesitate to say that two methods would give you something exactly the same. Essentially, I'm giving you a non-answer because I don't really know. Yeah. Okay, so let's keep moving. Okay, so there's all kinds of cool stuff you can do in global illumination. Here's another good example of global illumination known as subsurface scattering. In this case, maybe your path doesn't just like bounce or change its angle when you hit a surface. Maybe it just does so arbitrarily in the interior. So here's a nice example of what that looks like. So right, so in rendering marble is one of these materials. Your body is another, where like if you hold a light bulb up to it, then you'll see light coming out even though you're holding the light bulb right against the surface. And the reason is the light is going into the surface, bouncing around inside of this medium inside of you, like your fluid and God knows what else, and then coming back out. And you can, all these global illumination algorithms we've already talked about are totally relevant here, right? Like in this case, maybe I scatter my photons and then I kind of randomly have them swim around in the interior for a while before I stop, right? Or before I, leave the surface again. And that's a totally reasonable thing. These are extremely expensive rendering algorithms, but they can get very cool effects. Of course, these are really important, especially for rendering human skin. It turns out, fun fact, that your skin has a ton of subsurface scattering effects. And for whatever reason, your brain happens to be kind of sensitive to them, which is really frustrating for rendering because it's an extremely expensive effect to capture. So in terms of, like, we'll talk a little bit about the uncanny valley later in this course, when we very briefly mention perception issues, right? The uncanny valley being that, like, certain visual effects your brain doesn't notice and certain ones your brain is, like, really, really sensitive to. Subsurface scattering is one of these. So, like, when you see rendered humans and there's no subsurface scattering, so they're kind of like porcelain looking, this really creeps people out. Like, this is one of these effects that really somehow your brain is like vomiting and getting really upset. Okay, and this is just the beginning. You can easily take an entire graduate course in computer graphics and learn like all kinds of cool rendering techniques. Like, this is a thing people study quite a bit. For instance, maybe you do like bidirectional path tracing. So like you send some things from the camera, some from the light. You try to kind of make them, meet up. There's metropolis lights transport, which is like a specialized kind of randomized thing. I think it was invented by my PhD advisor, so that's kind of cool. And then there's this entire other class of algorithms out there, like radiosity and so on, that actually like write down the rendering equation as a system of equations and try to solve it, which is just crazy. The basic takeaway here and the takeaway of the last several lectures is that rendering is one giant integral, and it's like integrals all the way down, right? Like it's integrals of things that were themselves integrals and bouncing every which way, and you can integrate over the volume if you want to do subsurface scattering, plus over time if you want blur, and so you should be writing these things all the way across the board, and lens depth of field effect is another one, so on. So, and moreover, when we do our integration, it's over all kinds of different domains, right? Like the plane and time, spheres, light sources, and so on. So maybe it's worth thinking about integration a little bit. It seems is the main takeaway here, and so that's what we'll discuss a bit today. Here's another good example. So here we're rendering glossy reflections. So remember, like one way that we can do that is, bounce your ray off and then randomly perturb its direction a little bit to get the sort of glossy effect. And of course, if you do that with one sample per pixel, it looks pretty terrible. As you increase, you get this really nice kind of brushed effect. One thing to notice is that there's a lot of different trade-offs here between like the variance and the level of noise, the standard deviation, and so on. And there's some function of the number of rays. So it's worth spending 15 minutes to just talk about like, well, how do you choose how many rays you need in practice, and like what do you expect happens, right? So that's what we'll do now. So in case we forgot what an integral is, let's remember what that is real quick. So here's a function, and our job here is to estimate the area under the curve. We're going to start easy. Of course, typically in this class, we're not just integrating over a line like you did in calculus class, but rather over hemispheres and all that other stuff. But basically the same principle occurs. And once again, this is a continuous problem, but in rendering, what is this function? It's like the color of an incoming ray. It's extremely like discontinuous. We don't know anything about it. And so the reality is we have to discretize, right? And your calculus class probably already covered all kinds of different integration tricks, but somehow we haven't really used them so far, right? Like, you guys remember all this stuff, like trapezoid rule, Simpson's rule, so on? So far, our integration strategies look something more like this, right? Like we just randomly draw a bunch of points and just average their value, multiply it by the width of the interval, and that's kind of like the 1D analog of the integral that we're computing. But nobody told us that we had to do that, and it is worth thinking about other alternatives. And indeed, if you dig into the rendering literature, into a graphics textbook, you'll see many, many options out there. Right, so yeah, so here's a formula sort of what we've done so far, right? Which is if I want to integrate over some domain S, one way to do that, to integrate a function, is you randomly, with uniform probability, generate a bunch of points xi in my domain, average their value, and kind of scale it by the volume of my domain. Is everybody convinced that this is roughly an approximation of the integral? So this thing is, this is called the Monte Carlo approximation of the integral. Essentially, the relevant question for rendering, if I want to know like how much computation is what? Like what is this number n, right? How many samples should I send out? Does anybody know like what the convergence rate of this kind of algorithm is? In other words, like roughly the approximation quality as a function of n? Well, it turns out that the error decreases roughly as a fraction, as a function of 1 over the square root of n. In other words, like that's a number that goes to 0 as n goes to infinity. So this is giving you some kind of asymptotic understanding that like if I want 2 times the quality, I need 4 times the number of samples. If I want 4 times the quality, I need 16 times the number of samples, right? Like look, there's a square in there. That's the tiniest bit frustrating, right? Because that means that like to double, there's like an exponent hiding in there when I want to increase my quality. Yep. Right, and so this is a blessing and a curse depending on who you talk to. So on the one hand, okay, it's kind of nice that we have some bound. We have some intelligent way to choose a number of samples. In other words, I want the quality to be this much better. How many samples do I expect to need? The other kind of surprising fact about Monte Carlo integration, my integrals in this class are over very, very high dimensional functions, right? I mean, it could be the cross product of space and time and different points in space, whatever. One thing that isn't here is the dimensionality. And that's this kind of amazing fact about Monte Carlo integration, is that 1 over the square root of n has nothing to do with the number of integrals that are sitting on the outside. This is different than, for example, like if I want to approximate by, I don't know, placing a grid of numbers, right, and then sampling on a uniform grid, adding those numbers by, dividing by the size of the grid. Well, the number of grid points I need grows in the dimensionality, right? Like if I want an n by n grid, that's way less computation than an n by n by n grid, and so on. But that's still, if you work out your Taylor series, the convergence rate. The amazing thing about Monte Carlo is that it's always 1 over the square root of n. There's no dimensionality there. But square root of n shrinks pretty slowly. So that's the sort of trade-off. As an example, by the way, here's a Monte Carlo computation of a kind of a complicated integral. So maybe I want to estimate the area of a circle. What could I do? I could randomly draw points in the unit square, check if they're inside the circle, count how many are inside, how many are outside. Really exciting material. Multiply it by the area of the square, which is just 1, and get the value that I want. I think I'll let you guys try that at home. I think hopefully you guys have all seen an experiment that looks like this, and you get a little plot of the error of your estimate, and of course it converges to pi eventually, or pi over 4. So there's a reasonable question here. I mean, this is one integral, but like maybe there's some other approximations out there that make more sense. Like I think before we were asking, like if we know that our BRDF has like a giant lobe over here and then zeros everywhere else, does it make sense to send out rays in those other directions? Probably not, right? On the other hand, it's going to make my integral formula more complicated because now I've got to account for the fact that my distribution of rays isn't uniform, and so if I want to increase the degree of quality using techniques like Simpson's method or whatever is probably not the way to do it because now it depends on dimensionality. So we kind of like this Monte Carlo stuff. The problem is just that it's noisy and slow, and so we'd like to improve that. Right? So there's our basic setup. And now we're going to talk a little bit about some strategies for sampling, although we're running a bit late. So here's an example where we've used the same number of samples per pixel. On the left-hand side, it's just the uniform scattering strategy. And on the right-hand side is using strategies like what we talked about, where you're going to kind of concentrate your samples where you think that you're going to get the most contribution to your integral. Okay. So in other words, the question we want to answer is, are uniform samples the best that we can do? The answer is obviously no, because I'm asking it. Okay. So here's an example. So let's say that I want to integrate a function in 1D, just for some intuition. Where do I need a lot of samples and where do I need relatively few? Do you have any ideas?
I guess where the derivative is higher, you want to take more samples.
Yeah, so, right, so exactly. So when my function is changing really, really quickly, applying actually some intuition we already developed in our last class, right? I need a lot of samples to resolve what's going on. When my function is wiggling really, really fast, that's probably where I want to put all of my samples. My function is relatively flat, right? Then a few samples will do because I kind of know in between them that I can do some reasonable kind of interpolatory behavior and nothing much is going to change. Right? That's the basic point here. So, right, so for example, let's say I'm rendering glossy reflection, right? So remember, glossy reflection has this BRDF where like mostly it's just this lobe that is like right where the reflected thing is, but it's not just one pointy line because it's a little bit brushed. Where should I probably put most of my samples? Yeah, right on the doodad that's coming out of this thing, the lobe, right? Should I put all of them there? No, right? I mean, there's still a non-zero sphere worth of other stuff, and it could be that like maybe there's like a really, really, like I'm pointing a laser in this direction, and completely neglecting it will cause an error. Right, and so a very typical thing to do would be to generate samples that are maybe proportional, have probability density proportional to your BRDF rather than just uniformly, because that's where you expect to get most of the contributions to your integral. On the other hand, when you do that Monte Carlo formula, of course, what do you have to do? You have to weight the points according to their probabilities, right? That's how that works. So here's an example of what this looks like. So here, in both of these images, we have 5 samples per pixel, rendering this kind of brushed, I don't know, what is this, face thing? So here, the samples are completely uniform over the sphere, so with pretty high probability, they go into a place that gets multiplied by a small number in the BRDF. Down here, they're chosen proportional to the BRDF, and you can see already that the noise has decreased in the rendered image. Does that make sense? It's a pretty simple change. So here's 25 samples per pixel. If you take a look at the bottom image, you can see that it's basically already converged. And here is 75. And already, like with 75 up here, by the way, it looks like I've increased my number of samples a lot, but of course, remember there's this 1 over square root of n. The difference between 25 and 75 samples per pixel is actually not that big. So being careful about your integral really, really matters here. Okay. This is called importance sampling for obvious reasons. You're sampling based on the importance you think of your direction. Remember, this is just a hypothesis, right? We don't actually know the incoming color, because if we did, we'd already be using it in our rendering. But there's some pretty reasonable distributions we can choose that sort of concentrate samples where we think it's going to matter, typically aligned with the lobes of the BRDF, or maybe where we know the light source is. So if we're going to do that, now we have this p function here. Remember what our function was before? We just take a bunch of samples, average the value, multiply by the volume. Now what do we have to do? Well, if I am way more likely to choose samples, right? So p is big. So this would be like in the lobe of the BRDF. I should actually discount my value of f a little bit. I should divide by it. Why is that? Yeah.
You're probably going to have more shooting networks, so it's disproportionate.
Exactly. So I'm taking an integral over something, like a circle or a sphere. I have a bunch of samples over here. The contribution to my integral of any one of those samples is inversely proportional to their probability, because there's just more of them, right? There's the higher detail. Whereas if I have a sample over here, his job is to account for this entire piece of the circle, so it needs a bigger weight. You can work out that this is really the proper estimator here. So of course, the problem of designing p's, you can use any p that you want, and in theory it'll converge if you generate enough samples, but you really want to choose one that sort of mimic the behavior of your BRDF, your reflectance, maybe something about your scene. And this is really an art rather than a science. And nothing is perfect, but there are a lot of things you can do that are better than uniform. So here's another example of what this looks like. So here's sort of I think there's just a very simple importance weighting one. Here's a slightly smarter one. You can see that it's a nice smooth image. These are all in the details, by the way. These are the kind of things where you have to really take a magnifying glass to your image to detect what goes wrong. Questions so far? Okay, in addition to that, remember we've talked about doing integration over pixel space for stuff like anti-aliasing. There's sort of a weird push-pull that happens in that domain, which is, on the one hand, theoretically, I can just randomly generate points until the cows come home, and I'll get a nice approximation of my integral. On the other hand, remember that one of the sources of noise was the fact that every once in a while I have a pixel who sends out a ray, and it's just so decorrelated from its neighboring rays, it gets a totally different color. Right? And so one thing you might do is try to compromise between the regularly spaced samples on the one hand, which had the advantage that somehow nothing totally crazy can happen. You won't have an outlier pixel. On the other hand, having completely regularized stuff leads to these moire patterns we talked about in the last lecture. So one thing to do is a trick called stratified sampling, which is sort of halfway in between, where maybe I take a pixel, or the hemisphere, by the way, there's nothing special about pixels here. I divide it into subpixels, and then within every subpixel, I uniformly draw the location of my ray. So now I have some guarantee that these samples all don't cluster by accident, which remember, there's millions of pixels in an image. So if I'm generating, 16 samples, there's probably one pixel in my image whose samples look something like this, which is going to lead to some yucky outlier, right? So this is still randomized, but I have some bound that the points aren't totally clustered together. And there are all kinds of different strategies for stratified sampling. I've frankly never encountered a world where one is way better than the other, but all graphics classes are somehow morally obligated to teach all of these things. There's a lot of strategies here. So another one which is kind of funny is you think of your pixel as a chessboard, and now you randomly draw somewhere to put your sample. Then you they call this Rook's sampling. So now you X out that piece of the grid, and then the next thing you randomly draw is from the remaining ones, and you repeat that process. So you never get two things that share a row or a column. Yep. Oh, sorry, queens, rooks, right? Rooks go this way. Yeah. Yeah, I guess you rotated it 45 degrees. You get queens. Right. So these sort of strategies for stratified sampling are nice for low-dimensional domains. Not high dimensional ones, because I remember I needed a grid to do that. But there's some like kind of nice trade-off between regularly sampling on the one hand and randomly sampling on the other. So here's some nice anti-aliased image. Any questions so far? Cool. So there's all kinds of different references out there for this stuff. Eric Veitch is a very famous person in this area. We've got an Academy Award for these kinds of techniques. Another good one is this physically based rendering book, which goes into this stuff in just truly excruciating detail. Or here's some other ones. This was my first computer science textbook. Okay, so in any event, with that, we're done for the day. Yeah, I'll see you guys Tuesday. So thanks for coming here. Sorry for the chaos outside of our classroom, and hopefully that won't happen again.